In this video, we're going to start Chapter 8 of the chemistry textbook. Chapter 8 is on the periodic relationships among the elements. And so once we're done with Chapter 8, we're going to have a much more extensive understanding of the periodic table. Now, by the end of Chapter 8, we won't be completely done learning and understanding the periodic table. This is something we're going to continue to do throughout the textbook. But so we were introduced to the periodic table in Chapter 2. We had a brief introduction to the fundamentals. And what we're going to be doing in this chapter is just really diving into the periodic table in significantly more detail. Diving into why it's organized the way it's organized, why the elements are organized the way they're organized, why it's labeled the way it's labeled, the column labels, the row labels, the different categories of elements, how we can use the periodic table to understand chemical and physical properties, to understand why certain things happen in chemistry. Okay, so we're going to start by revisiting the history and development of the periodic table. We touched on this a little bit in Chapter 2. We're going to go through it in more detail here at the start of this chapter. Okay, so it says, many of the chemical properties of the elements can be understood in terms of their electron configurations. Because electrons fill atomic orbitals in a fairly regular fashion, it is not surprising that elements with similar electron configurations, such as sodium and potassium, behave similarly in many respects, in that, in general, the properties of the elements exhibit observable trends. Chemists in the 19th century recognized periodic trends in the physical and chemical properties of elements, long before quantum theory came onto the scene. Although these chemists were not aware of the existence of electrons and protons, their efforts to systematize the chemistry of the elements were remarkably successful. Their main sources of information were the atomic masses of the elements and other known physical and chemical properties. Okay, so what did they just say here in this paragraph? At the beginning of this paragraph, what they're saying is that the properties of elements, chemical and physical properties, we're going to be able to mainly associate with the electron configurations of the elements, which, as you can imagine, if that's what's dictating the different physical and chemical properties of elements, that's also going to be what the criteria we use to organize the periodic table. Similarities in electron configurations. Okay, but in the second part of this paragraph, what they're saying is that when they were originally discovering elements, before they ever discovered the electron and the proton or quantum theory, for some reason, their efforts to systematize the chemistry of the elements was still very successful. So why was that the case? I mean, it's not like it happens all the time in science, where we can't figure something out, where we're not successful with it at all, and then eventually as technology increases, we figure it out. So it didn't have to be the case that they had to start off successful with this. Successful with, they were discovering elements and they were just analyzing them, trying to put them into categories, group them to see if they could find trends. And in the beginning, before they knew anything about electrons and protons and quantum theory, they were very successful at doing this. Why? Okay, well, let's see. It says their main sources of information were the atomic masses of the elements and other known physical and chemical properties. So when it comes to physical and chemical properties, well, yeah, so they have an element that they discovered. They can see if it's a gas or a solid or a liquid. They can see if it has an odor, if it's reactive or not reactive. The physical and chemical properties are evident. So they have that information. Okay, but what they were also able to do was measure pretty accurately the atomic masses of the elements. That's the information that they had. So what you can think about is, from the beginning, you could organize these elements that you've discovered based on their similar chemical and physical properties. You could do that from the beginning. But it's much more powerful if, in addition to organizing the elements that way, putting them into these similar groups based on chemical and physical properties, All the stable gases go in this group. All the stable metals go in this group. All the reactive metals go in this group. It's powerful if, at the same time, in addition to that, you have some measurable property of the elements that also coincides with those groups, right? Because again, you could put the elements into the similar chemical and physical property groups. That's not hard. What's hard is to do that and at the same time have some other measurable property that also coincides with those groups. And that's what they're talking about here. Their efforts to systematize the elements in the beginning, before they knew about electrons, protons, and quantum theory, was successful because what they could do is they could order the elements by atomic mass. So the first element was this atomic mass. The second element was the next heaviest element. The third element was the next heaviest element. When they ordered them this way, there was also a pattern to where it was like every eighth element had the exact same or very similar properties, right? If you got to a very stable gas, then go 8 elements later, 8 heavier elements later, and you got another very stable gas. Go 8 elements heavier than that, you have another very stable gas. The same thing with carbon. That would be, the fifth heaviest or the sixth heaviest element. This at room temperature and pressure, it's this solid but not a metal. Okay, go 8 elements heavier than carbon, you get another solid that's not a metal, similar to carbon. Okay, so that's interesting. Why were they successful with organizing these elements based on atomic mass? Successful at sort of systematizing all of the elements as a group, organizing them. Because if you think about it, this is not very intuitive. In our experience of everyday life, if something has more mass, that doesn't change its chemical and physical properties. I could have a container of syrup in my pantry or a big vat of syrup in a plant. It's still just syrup. In general, things don't change their color, their smell, whether or not they're a solid, liquid, or gas just because you have more of it. So you can think about how it wouldn't necessarily be that intuitive that organizing these elements, ordering them based on atomic mass, would result in this synchrony of chemical and physical properties in this way that you could clearly see. Maybe some other property, but not mass, right? Okay, so it says, in the 19th century, when chemists had only a vague idea of atoms and molecules and did not know of the existence of electrons and protons, they devised the periodic table using their knowledge of atomic masses. Accurate measurements of the atomic masses of many elements had already been made. Arranging elements according to their atomic masses in a periodic table seemed logical to those chemists who felt that chemical behavior should somehow be related to atomic mass. So, yeah, I'm not a professional chemist. My guess would be that they didn't initially think it would be logical to organize these elements in terms of atomic mass. That's just a property that they could accurately measure. And so they were just playing around with anything they could play around with to try and find some trends. And then they organized it based on atomic mass and said, well, look at this. Every eighth element is doing this. Every eighth element, you've got this like synchrony in physical and chemical properties. So there must be something there. Okay, in 1864, the English chemist John Newlands noticed that when the elements were arranged in order of atomic mass, every eighth element had similar properties. Newlands referred to this peculiar relationship as the law of octaves. However, this law turned out to be inadequate for elements beyond calcium, and Newlands' work was not accepted by the scientific community. Yeah, so if we take a look here, organizing by atomic mass was remarkably successful, but it wasn't foolproof, because if we look here, look at argon, its atomic weight is 39.948, but then if we come to the next element in line, potassium, we have 39.098. Potassium weighs a little bit less on average. So if we're being strict about the atomic mass criteria, potassium should be here and argon should be here. Okay, but what we're about to read is that what you can think about is that there was a back and forth between these different theories of how to organize the periodic table. some people were saying, no, I don't care that potassium weighs a little bit less than argon. We're leaving potassium here. It makes more sense to leave potassium with these unstable metals and argon with the very stable gases. That's got to be correct. And even though in some circumstances the atomic weights don't reflect this, that this should be the case, then maybe we're missing something we haven't discovered yet. But regardless, the periodic table should be organized this way. These patterns that we see here in physical and chemical properties are too powerful to say that we're going to put potassium here and argon here. Because we're about to read that. So one of the arguments was that it's too powerful for it to be the case that, so someone stated, okay, we have aluminum. We know aluminum, but we haven't discovered this element yet. But we can predict what this element is going to be like, the type of properties it's going to have. And then 4 years later, when they discovered gallium, they were dead on right. Okay, and so that's why, again, certain people were of the thought that, no, we do not want to move potassium to this noble gas group. There's got to be a rhyme and reason for why these patterns in physical and chemical properties are emerging. Okay, so it says, in 1869, the Russian chemist Dmitry Mendeleev and the German chemist Lothar Meyer independently proposed a much more extensive tabulation of the elements based on the regular periodic recurrence of properties. Mendeleev's classification system was a great improvement over Newland's for two reasons. First, it grouped the elements together more accurately according to their properties. Equally important, it made possible the prediction of the properties of several elements that had not yet been discovered. For example, Mendeleev proposed the existence of an unknown element that he called Eka aluminum and predicted a number of its properties. When gallium was discovered 4 years later, its properties matched the predicted properties of Eka aluminum remarkably well. So yeah, there you go. Chemists like Mendeleev and Meyer were of the train of thought that it's too powerful that these elements line up this way in terms of chemical and physical properties. So they were pushing to stay with that organization despite what the atomic masses might say to do in some circumstances. Okay, so Mendeleev's periodic table included 66 known elements. By 1900, some 30 more had been added to the list, filling in some of the empty spaces. The figure on the next page charts the discovery of the elements chronologically. Okay. So, yeah, here it shows the color coding is based on when the element was discovered. So these ancient elements like iron, copper, silver, gold, mercury, lead, tin, copper, sulfur, and they just show other time periods here. So, yeah, what they were, what you can think about is at that time, Mendeleev and Meyer wanted to keep the organization based on these columns here with chemical and physical properties lined up, and they were just discovering more elements and putting them into the correct column that matched up with the physical and chemical properties. Okay, but it says here, it gives the story about how there were still some issues with atomic mass not reflecting the order here. This is where it talks about the whole idea that potassium weighs less than argon. So what you can think about is that even though Mendeleev and Meyer wanted to keep these elements organized this way into these groups here, these columns, there was still an issue in that, okay, but then what's the underlying measurement of these elements that will agree with this organization? Because what you can think about is that, like, yeah, so we know aluminum exists. So we've discovered aluminum, right? Now I'm going to predict what this element's going to be, the properties of it. Okay, then we discover gallium and I was right. It's a shiny, lightweight metal, whatever. Well, okay, that's fine, but then what's my justification for putting gallium in this slot, right? What's the property I'm using? Because if there's no property I'm using, then we could have discovered gallium and said, oh, it's not like aluminum, so I put it into another group. What was the criteria they used to state what this element is going to be? And what it was at the time was atomic mass, because like we've talked about, atomic mass was remarkably successful at matching up with these groups here. So what they stated was that, look, when we get to this element in line in terms of atomic mass, we can predict what its properties are going to be relative to aluminum. And they were right. And they felt that was so powerful, they didn't want to start moving these elements out of these groups of corresponding physical and chemical properties. But the question still remained, what's the correct property to use to organize these elements in order? And this property would help to explain why columns of elements like this had the same physical and chemical properties. And it would explain why the elements are the way they are. Right? That's what we're trying to do. We're trying to understand matter and how it behaves, why it behaves the way it behaves. Okay, so it says, using data from alpha particle scattering experiments, Rutherford estimated the number of positive charges in the nucleus of a few elements, but the significance of these numbers was overlooked for several more years. So what they're talking about here is, if we come back to chapter 2, so Rutherford's experiment was how the nucleus of the atom was discovered. He was shooting these alpha particles. So alpha particles come from radioactivity, extremely high energy. He was shooting these alpha particles through this thin gold film, and what he discovered was that most of the particles would just go straight through, unhindered. But every now and then, a particle would almost like hit a brick wall and get deflected straight back from where it came. These extremely high energy alpha particles. And that's how they discovered the nucleus. The atom was mostly empty space, and at the center was this extremely dense, positively charged nucleus. And it was positively charged because alpha particles are positively charged. Okay, so the conclusion was that the nucleus was composed of positively charged particles called protons. Okay, so now what it says is that at the time, Rutherford also, he took it a step further and estimated the number of these positively charged protons in the nucleus for a few elements, but it says the significance of these numbers was overlooked for several more years. So what they're talking about is that this was significant because in 1913, an English physicist, Henry Moseley, thought maybe if we could get the count of the number of these positively charged protons in the nucleus for the different elements, maybe that's the correct criteria to use for ordering the elements. And what you can think about is that this made sense from the perspective that they knew that the atom was mostly empty space. They knew that electrons were negligibly light compared to what was in the nucleus. Okay, so the count of the number of positively charged particles in the nucleus would be like a parallel to atomic mass. Now you might be saying, well, wait a minute though, but what about the neutrons? That's true, but if for each element you're just forgetting about the neutrons and strictly doing a count of the protons, you're still ordering it in terms of, in some sense, in terms of increasing atomic mass. Okay, and so what Henry Moseley did was, it says he discovered a correlation between what he called atomic number and the frequency of X-rays generated by bombarding an element with high-energy electrons. Moseley noticed that the frequencies of X-rays emitted from the elements could be correlated by the equation. So he's bombarding different elements with high-energy electrons, and then what happens is they emit these X-rays, and he's recording the frequency of the X-rays. So he has this equation here. It has the frequency of the X-rays, these constants A and B, which were the same for any element, and then what he called the atomic number Z. Okay, so it says, V is the frequency of the X-rays, A and B are constants, the same for all elements, and thus from the square root of the measured frequency of the X-rays, we could determine the atomic number of the element. So it doesn't go into details here on how he was able to conclude that atomic number did represent the number of those positively charged particles in the nucleus, the protons, but he was able to show that's what it was. So that's how he could calculate the atomic number. Okay, now it says, With a few exceptions, Moseley found that atomic number increases in the same order as atomic mass, which makes sense, right? We would expect the atomic number, as atomic number increases, the atomic mass just follows in parallel. But the fact that there are a few exceptions, that's not that unbelievable as well, because the neutrons could slightly vary. Okay, but what they showed was that this accounted for the discrepancies. Even though potassium weighs less than argon, potassium does have a higher atomic number than argon. And so using the atomic number to organize the elements solved the issues across the board. Okay, and so that's how we discovered that the periodic table, that the elements in the periodic table need to be organized in order of increasing atomic number. If you do that, that's how you're going to get this beautiful alignment in physical and chemical properties. You know, with respect to it's periodic. Everything's periodic. If you line them up in terms of atomic number, you get these columns like this with these matching physical and chemical properties. Okay, so a modern periodic table usually shows the atomic number along with the element symbol. As you already know, the atomic number also indicates the number of electrons in the atoms of an element. Yeah, because the charges need a balance. Electron configurations of elements help to explain the recurrence of physical and chemical properties. The importance and usefulness of the periodic table lie in the fact that we can use our understanding of the general properties and trends within a group or a period to predict with considerable accuracy the properties of any element, even though that element may be unfamiliar to us. Yeah. Okay, but we still want to think about what you can imagine is at the time, right when this whole atomic number idea for organizing the elements was discovered. So maybe they hadn't really developed quantum theory much at that point, and not much was known about electron configurations at that point. What you can think about is, so you would be thinking, okay, so the number of positively charged particles in the nucleus is the correct way to organize these elements, the order of organizing these elements. So it explains why the atomic mass was successful at organizing the elements, right? It's not that the atomic number corresponds to the mass of the element, not at all. It's really the protons and the neutrons together is what dictates the mass. But it makes sense that it was a coincidence that the atomic number and the atomic mass line up in sequence a lot of the time. But it really wasn't the mass that was the correct way to organize these elements. It was the number of positively charged particles in the nucleus, protons. Okay, but still, what does that have to do with, why does that cause the elements to line up like this periodically? To where you get these columns here of these matching chemical and physical properties. Well, you would still be scratching your head a little bit. What does the number of protons in the nucleus have to do with physical and chemical properties like this? Okay, well, we know where this is coming from. And so let me go ahead and restate this for you, just to make sure it's clear. Okay, where this is coming from is the Aufbau principle. Okay, let's come back to chapter 7. When we were learning how to create the electron configurations, okay, in section 7.9, we talked about the building up principle, this Aufbau principle. It says that as protons are added one by one to the nucleus to build up the elements, electrons are similarly added to the atomic orbitals. Okay, so when you first learn this Aufbau principle, it seems kind of trivial. Okay, but what it's saying is that to build the electron configuration of an element, you just go proton by proton, electron by electron, and you just follow the orbital steps. 1s1, 1s2, then 2s1, 2s2, then the 2p, then the 3s, then the 3p. Right? Every proton you add another electron to that chain. Okay, now the reason we know that the reason you do this is because you're following the energy levels, and I mean that's a law of nature. You're gonna, the lowest energy state, the most stable state is what happens in nature. Okay, but what you can think about is that when they were solving the Schrodinger equation and getting the shapes of these orbitals and whatnot, it didn't necessarily have to be the case that these lowest energy states were based on this building up principle. Maybe when you got to element 20, things changed and the electrons changed configuration or something. It didn't have to be the case that it was just this simple building up. Add an extra proton, then just put an extra electron in the next step of the orbitals, one by one, one by one. You do that for all the elements, from element 1 all the way to element 100, whatever. Okay, and so that's where this periodicity in the physical and chemical properties is coming from. It's the fact that in the beginning, every 8th element, you're going to build up the electrons through the orbitals, through the energy levels in a similar way. Because you build up the electrons as you add more protons to the nucleus, you build up the electrons in the exact same way for all the elements. And so based on the constraints of the different orbitals, you're going to get some periodicity. Since the s orbitals can only hold 2 electrons and the p orbitals can only hold 6 electrons, then in the beginning, every 8th element, you're going to have electrons residing in similar types of orbitals. Okay. So now it says, figure 8.2 below shows the periodic table together with the outermost ground state electron configurations of the elements. The electron configurations of the elements were given in that table in the previous chapter. Yeah, we went through that table. Okay, starting with hydrogen, we see that subshells are filled in the order shown in figure 7.24. Yeah, so they're talking about that diagonal table. That's how you fill the subshells. So, okay, it says, let's come back to this first sentence. It says, in this periodic table here, they're showing the electron configurations, ground state, so the most stable state, only of what they're calling the outermost. So they're saying here, for boron, the outermost electrons are 2s2 and 2p1. Those 3 electrons. Okay, and this is really important for us to be clear on what exactly the textbook is referring to as these outermost electrons, as the outermost electrons of a given element. This is really important. So we can try and make an educated guess before we read deeper into this section. So maybe the outermost electrons of an element are any electrons associated with the highest principal quantum number of the electron configuration. Any principal quantum number electrons that are lower than the highest principal quantum number aren't considered outermost. Okay, so let's see. That works for hydrogen and helium. That works for this, for period 2. That works for period 3. Okay, but then we get to scandium, and no, according to this table here, the 3d1 electron is included in this outermost category for scandium. Okay, so it's not the case that it's strictly the highest principal quantum number electrons that are considered outermost. Okay, so let's keep that in mind as we continue with this section. Okay, now it said, starting with hydrogen, we see that subshells are filled in the order shown in that diagonal chart, but yeah, we talked about that in detail. Yeah, in general, you're going to follow that diagonal chart order, but there's exceptions you have to deal with when in particular in relation to the d orbitals and the f orbitals. But we talked about those exceptions. Okay, so now it says, according to the type of subshell being filled, okay, the subshell being filled. Remember, a subshell is a principal quantum number and an orbital shape pair. The 2p subshell, the 4d subshell, the 5f subshell. So according to the type of subshell being filled, the elements can be divided into categories. The representative elements, the noble gases, the transition elements or transition metals, the lanthanides, and the actinides. Okay, so if we look at this periodic table here, So different periodic tables are going to be categorized in different ways. This is a more detailed categorization than what the textbook just described. And the reason is because the textbook's giving us more of an introduction. Okay, so here, yeah, we have the transition metals, but then they label these gray metals post-transition metals. Here's metalloids, noble gases. It's calling these reactive non-metals. You have alkali metals, alkali earth metals. Okay, but the categories that the textbook just laid out were some simpler categories that are still really useful. So the representative elements, the category they're referring to in that case is, so when we're thinking about these categories, they mentioned, let's come back here, they mentioned, it said according to the type of subshell being filled, we put the elements into categories. So according to the type of subshell being filled, what are they talking about there? What they're talking about is the last subshell being filled, the subshell that's going to have incompletely filled or partially filled orbitals. So yes, if we look here at antimony, okay, well, to apply the electrons to the atom of antimony, well, yeah, you do the 1s, you do 1s2, 2s2, 2p6, 3s2, 3p6. I mean, you're filling up the s's and the p and the 3d orbital, the 4d orbital. That's true. But what they're talking about for these categories is it's that last orbital you're going to be filling up, to where maybe you fill up the entire orbital and you're done. Like with the noble gases, you do fill up the entire p orbital, but that's still, even in the case of noble gases, that's still the last orbital you filled up. Or in most cases, you're going to have you're not going to finish filling up that orbital. It's going to be partially filled, or you're going to have some unfilled orbitals, right? With antimony, you would have, let's see, 2, 3, 4, it would be 5p3, right? That's what they're talking about in terms of the categories. Okay, so the representative elements, what the category of representative elements is when you have a incompletely filled s or p orbital. So these elements, as far as electron configurations you can think about, are easy to work with. It's all of these elements. So not including the noble gases. Noble gases are pretty easy too, just because the noble gases are they're completely filled. But all of these elements, these representative elements, what you can think about is you're not having to deal with any incompletely filled d or f orbitals. That's the characteristic of the representative elements. But same idea with the noble gases, but the noble gases get put into their own group, right? So these are nice when doing electron configurations. You just follow that chart. Okay. Now the noble gases, okay, so it says the representative elements, also called the main group elements, are the elements in groups 1a through 7a, all of which have incompletely filled s or p subshells of the highest principal quantum number. Okay, so yeah, let's come to this chart here. We're going to learn about these column labels in a second, but they're saying groups 1a through 7a. Okay, and so they have incompletely filled s or p subshells, but it also says of the highest principal quantum number. So what do they mean by the highest principal quantum number? Okay, well, it's always going to be the case with the representative elements that these final orbitals that are going to be either unfilled or partially filled are all going to have the same principal quantum number. It's going to be the highest principal quantum number. What they're saying is that with the representative elements, you're never going to have a case where, okay, like with, what was it? With chromium, the electron configuration was like 4s1, 3d5. And then the d orbitals were all half filled. In that case, you have a half filled 4s orbital and a half filled 3d orbital. So you have two different principal quantum numbers that aren't completely filled. You see, with representative elements, it's always going to be the case that, so here you're going to, the unfilled orbitals are going to be something like 2s or 2p. Here 3s or 3p. Here 4s or 4p. Here 5s or 5p. You're never going to have this mixing of principal quantum numbers in terms of the orbitals that aren't fully filled. Okay, now it says, with the exception of helium, the noble gases all have a completely filled p subshell. Yeah, so the noble gases will have a completely filled p subshell, except for helium, which is going to have a completely filled 1s subshell. But still, you can think about all of the noble gases have completely filled orbitals. Okay, the transition metals are the elements in groups 1b and 3b through 8b, which have incompletely filled d subshells or readily produce cations with incompletely filled d subshells. The non-sequential numbering of the transition metals acknowledges a correspondence between the outer electron configurations of these elements and those of the representative elements. Okay, so the elements in blue are the transition metals, but these don't include this last column here. And so what makes an element a transition metal is that it has an incompletely filled d subshell or readily gives rise to a cation that has an incompletely filled d subshell. Okay, and so with that, you can think about why these are not technically considered transition metals, because they have the entire d subshell filled. Well, at the same time, they don't readily give rise to cations that make the d subshell partially filled. Okay, now they also talked about these column labels. So if we look, there's two separate sets of column labels shown here. On top, each column is just numbered in order, 1 to 18. On the bottom, you've got a number and a letter. So it goes 1A, 2A, and then 3B, 4B, 5B, 6B. And this makes sense because they're just, the B is to acknowledge that you're dealing with the transition metals or this middle block of elements here. And the A just acknowledges you're dealing with a representative element or a noble gas. That makes sense. So 1A, 2A, 3B, 4B, 5B, 6B, 7B. But then all three of these columns are 8B. And then we don't go to 9B, we go to 1B, then 2B. And then when we come here, it's not like we go to, okay, is this going to be 9A? No, this is 3A, 4A, 5A, 6A. So what's up with the numbering here? And then why does this top labeling scheme seem to want to do away with this non-sequential numbering and the letters? Just go 1 to 18, simple as that. Okay. Well, yes, the letter is just to acknowledge if you're dealing with a column in the transition metal middle region or one of the outer representative element noble gas regions. That's the purpose of the B and the A. Okay, but what the numbers are doing is it's giving you a correspondence between a column in the transition metal region and a column in the representative element region, to where the elements in those columns have the same number of outer electrons. Okay, again, we saw how the textbook seems to state the outer electrons of an element. We haven't talked about it officially yet, but so again, if we look here, scandium, the outer electrons are these 4s2 electrons and the 3d1 electron. There's 3 outer electrons. And that would be the same for every single element in this column. 3 outer electrons. Okay, so this is 3b. Now, if we look at 3a, how many outer electrons do the elements in this column have? Well, if you're not dealing with a transition metal or any metal in the middle here, even this column, if you're dealing with an incompletely filled s orbital or p orbital or a noble gas, then it's just so here boron, it's the 2s, the two 2s electrons and the 1 2p electron. And it's the same for every element in this column. There's 3 outer electrons. And so that's the purpose of this numbering scheme. 4b, 4a, there's 4 outer electrons. Same with 5b, 6b, 7b. And then we can think about how when you get to 8 outer electrons, it gets a little tricky. Because it's, okay, so I guess these match up with the noble gases. I mean, but not really. I mean, this column has 8 outer electrons. This has 9, this has 10. But you can't label this column 9b or 10b. I mean, what's that going to match up with in the representative elements? And this gives you a sense of why this top labeling scheme is perhaps preferred. Because when you get to these elements here, there is nothing that this labeling these 8b kind of doesn't make any sense. In fact, even saying that these elements do have 8 outer electrons, just like the noble gases, but I don't know if you would compare these elements to the stable noble gases. You still have an incompletely filled d orbital with all 3 of these elements, right? Okay, but now, so what about these two? Why is this 1b? So I guess this matches up with 1a. Yeah, it does, because if you remember, so copper was the way you fill copper. So just following the standard chart, that diagonal chart, you would do like this. You would do, well, you'd fill this one, it would be like this. And then you do like that, right? But in actuality, this is one of the exceptions, and the electron configuration turns out to be like this. You fill up the entire d orbital, and so what are you left with? This single unpaired electron in the 4s orbital, just like all the alkali metals, right? It's a similar idea with group 2b and group 2a. They both have a completely filled s orbital. Okay, so now it mentions here that it says it should be noted that the designation of A and B groups is not universal. So in Europe, they use the 1A, 2A, 3B, 4B, the number and letter labeling scheme, but they just switch. They have the transition metal region labeled with an A and the representative elements with a B. The American convention is just it's this number then letter, but with A, using A for the representative elements and B for the transition metals. And the top row, 1 to 18, is based on, so the International Union of Pure and Applied Chemistry has recommended numbering the columns sequentially with just the numbers. The proposal has sparked much controversy in the international chemistry community, and its merits and drawbacks will be deliberated for some time to come. In this text, we will adhere to the American designation. So, yeah, I mean, you can think about why perhaps they wanted to do away with the letters here, again, because, I mean, even comparing this 2B to 2A here, I mean, 2A has a large principal quantum number. So, okay, comparing calcium to zinc. Calcium has, it's a 4s2, and that's it. Zinc is going to have a 4s2 3d10. To me, it seems as though zinc's going to be more stable than calcium, because you've got this 3d subshell and 4s subshell with close to the same energy level, and it's complete. They're all completely filled, as opposed to with calcium, you've got this lone 4s subshell that's completely filled. And then again, with this group of 8 Bs here, if you use this labeling scheme with the letters, the numbers and the letters, it's implying that these 3 columns are similar to the noble gases. No way. These are unfilled d orbitals. This is the noble gases are famous for being just completely filled up across the board. Like, you couldn't compare cobalt or iron to krypton. Krypton's got a completely filled 4s and 3d and 4p orbital. That's different than these 3 columns, the outer electrons. So, I don't know. All right. The lanthanides and actinides are sometimes called F-block transition elements because they have incompletely filled F subshells. So, yeah, here's the lanthanides, here's the actinides. And just note that with the transition metals, they're characterized by incompletely filled any D subshell, 3D, 4D, 5D, whatever. The lanthanides is just speaking about the 4F subshell, and the actinides, the 5F subshell. Okay, if you've got any element that has an incompletely filled 4F subshell, either in its ground state or it readily gives rise to ions that have an incompletely filled 4F subshell, then that's a lanthanide. If it's dealing with a 5F subshell, that's an actinide. Okay, the chemical reactivity of the elements is largely determined by their valence electrons, which are the outermost electrons. So here we go. We've unofficially been talking about these outermost electrons, and so now we're getting a more official look at these outermost electrons. What's classified as the outermost electrons of an element is very important, very important. So we're going to want to be very clear if we're given any element, what are its outermost electrons? How many are there, and what are they? These are called valence electrons. It's extremely important. I'll say that again. It's very important that we're extremely clear on, if we're given any element, how many outermost or valence electrons does that element have, and what are they? What subshells are they in? Okay, for the representative elements, the valence electrons are those in the highest occupied in shell. Okay, so with the representative elements, it's actually really simple. You just go to the highest principal quantum number in the electron configuration, and those are the outermost electrons. Okay, so if we come here with any representative element and the noble gases as well, so you have the entire electron configuration of that element. Okay, just go to the electrons that have the highest principal quantum number. So for this row, that would be the 2s and the 2p. Here, the 3s and the 3p. Here, the 4s and the 4p. You might say, well, what about the d's? Well, no, remember, this is 3d, right? If you wrote out the electron configuration for bromine, the final electrons would be, you'd have the 3d10, and there would be a 4s2, and there would be a 4p5. So you just look at the highest principal quantum number, electrons, and those are the valence electrons. Those are the outermost electrons when it comes to the representative elements and the noble gases. Okay, so now it says, all non-valence electrons in an atom are referred to as core electrons. Okay, so yeah, you have the valence electrons and the core electrons for an atom. Looking at the electron configurations of the representative elements once again, a clear pattern emerges. All the elements in a given group have the same number and type of valence electrons. The similarity of the valence electron configurations is what makes the elements in the same group resemble one another in chemical behavior. Thus, for instance, the alkali metals all have the valence electron configuration of NS1, and they all tend to lose one electron to form the unipositive cations. Similarly, the alkaline earth metals all have the valence electron configuration of NS2, and they all tend to lose 2 electrons to form the dipositive cations. We must be careful, however, in predicting element properties based solely on group membership. For example, the elements in group 4A all have the same valence electron configuration, NS2, NP2, but there is a notable variation in chemical properties among the elements. Carbon is a nonmetal, silicon and germanium are metalloids, and tin and lead are metals. Okay. So let's summarize what they just said here. They're saying that for the case of the representative elements, let's actually come back to this chart, this periodic table. So if we look at all of the columns of representative elements, they all have the exact same outer electrons, exact same valence electrons. And with the transition metals and the lanthanide and actinides, in general, that's going to be the case as well. There are going to be some slight exceptions here and there, but in general, that's going to be the case. Okay, what they're saying is that this is the reason why the chemical and physical properties of the columns of elements in the periodic table are so similar? This is the reason, right? That's a question we were talking about at the start of this video. The fact that the periodic table was arranged in a certain way to where you had this periodic alignment of chemical and physical properties. Every eighth heaviest element seemed to match up in chemical and physical properties, which then that was refined to where it really wasn't atomic mass, but it was atomic number was the correct way to order the elements to really make that be foolproof, to where truly if you order them based on atomic number, then every eighth element, et cetera, et cetera, et cetera, you're gonna have these columns of elements with similar chemical and physical properties. But still, even then, we never made an official statement. The atomic number arrangement was interesting, but we never made an official statement about what is it about these elements in the same column. What is the similarity from a physical perspective that's making their chemical and physical properties line up? It's here it is. It's the similarity in the outer electrons, the valence electrons, both the number of valence electrons and the orbitals in which those outer electrons are contained in. Okay, now they didn't make an official statement about how do you determine the valence electrons in the transition metals or the lanthanides and the actinides. So we'll come back to this more officially later, but we can take a look and get an idea of how this is going to work. So with the transition metals, the outer electrons are going to be all the electrons in the d orbital, the last highest principal quantum number d orbital, okay, and then the preceding s orbital. Okay, now with the lanthanides and the actinides, so there's not going to be many d orbital electrons in the outer shell of the lanthanides and the actinides, because remember these two rows get squeezed in here, so you don't fill up, let's see, we're at 3, 4, you don't fill up 5d and 6d until after you filled up 4f and 5f. So it's really going to be the 6s and the 7s electrons, maybe a d electron depending on the circumstance, and then just f electrons. Okay, but now they did mention that it says we must be careful, however, in predicting element properties based solely on group membership. So this isn't the group membership, the column membership isn't foolproof, because they give the example of group 4A, to where there's a notable variation in chemical properties among the elements. Carbon is a non-metal, silicon and germanium are metalloids, tin and lead are metals. Okay. As a group, the noble gases behave very similarly. Helium and neon are chemically inert, and there are few examples of compounds formed by the other noble gases. This lack of chemical reactivity is due to the completely filled NS and NP subshells, a condition that often correlates with great stability. Although the valence electron configuration of the transition metals is not always the same within a group, and there is no regular pattern in the change of the electron configurations from one metal to the next in the same period, all transition metals share many characteristics that set them apart from other elements. Okay, so yeah, here they're mentioning that when it came to the representative elements, you go down a group and it's that same valence electron configuration, but it's not quite that consistent when you go down a group with the transition metals. You'll see some differences here and there. And then, as we know, the same idea when you go across a period, it's not as regular and repeating as it is as you fill up the S and the P subshells. Okay, but what they're saying is even with that, all transition metals as a group share many characteristics that set them apart from other elements. The reason is that these metals all have an incompletely filled D subshell. Likewise, the lanthanide and the actinide elements resemble one another because they have incompletely filled F subshells. Interesting. Okay, representing free elements in chemical equations. So Having classified the elements according to their general ground state electron configurations, we can now look at the way chemists represent metals, metalloids, and nonmetals as free elements in chemical equations. Because metals do not exist in discrete molecular units, we always use their empirical formulas in chemical equations. The empirical formulas are the same as the symbols that represent the elements. For example, the empirical formula for iron is Fe, the same as the symbol for the element. Yeah, so what they're talking about here is if we're writing out a chemical equation and we're going to include in the chemical equation an element, so not a molecule or a compound, we're just thinking about representing a free element in a chemical equation, okay? Well, if it's a metal, then because metals are in these three-dimensional arrays that kind of extend indefinitely, there's no molecular units, then that's why with like ionic compounds, we don't use, it makes no sense to say something like Na2Cl2. No, you always, when it comes to metals, crystal structures, you always use the empirical formula because there is no like discrete molecular unit when it comes to a metal. It's just this infinite array. So you just say NaCl. And so, but we're not thinking about ionic compounds. We're not talking about ionic compounds here. They're saying, okay, if you're going to be representing in a chemical equation an element that's a metal, then you're just going to use its empirical formula, which for a single element would just be the element itself, right? It makes no sense to say Fe2, like it does make sense to say for in some non-metals to say something like O2, because you have with oxygen gas, they're in these molecular units of two oxygens for each molecule. And so the idea is if you're in a scenario where at some temperature and pressure, the most common elemental form of oxygen gas is, say, O3, then you would put O3. But like at room temperature and pressure or normal temperatures and pressures on Earth, it's the most common elemental form of oxygen is O2. So you put O2. And then again, if it's a metal, then you just put the empirical formula of the elemental metal, which is just the element name itself with a subscript 1. Again, because it's just the iron is just a three-dimensional array of iron in this big crystal form. There is no discrete unit of these iron molecules, so you just put the empirical formula, the smallest integer value. Okay, so that's metals. Okay, metals do not exist in discrete molecular units, so we always use their empirical formula. So, okay, yeah, let's take a quick look here. Remember, metals is everything to the left of this region. So these are all metals, well, not including hydrogen. These are all metals. Then you start getting into the transition metals and the metalloids. So you have to, once you start getting close to the non-metals, maybe some of the elements in these regions start to exist as discrete molecular units, and you'll have to potentially use this method for non-metals. So for non-metals, there's no single rule. Carbon, for example, exists as an extensive three-dimensional network of atoms, and so we use its empirical formula. Okay, so yeah, carbon, it's like diamond is a three-dimensional network as well. This just extends indefinitely, so you do a similar thing as with carbon, just put its empirical formula to represent elemental carbon in chemical equations. But hydrogen, nitrogen, oxygen, and the halogens exist as diatomic molecules, and so we use their molecular formulas. So you put H2, N2, O2, etc. The stable form of phosphorus is molecular P4, so you'll see that used in chemical equations as P4. For sulfur, chemists often use the empirical formula S in chemical equations rather than S8, which is the stable form. Thus, instead of writing the equation for the combustion of sulfur like this, they just write it in its empirical form. So, to me, I think it'd be more intuitive to use S8, just so you can get a sense of the physical reality of what's happening. All the noble gases are monoatomic species, thus we use their symbols. They're in this case, this isn't because it's a three-dimensional array like a metal. the reason why you're putting He1 in E1, it's because that's how they exist in nature as single monoatomic species. The metalloids, like the metals, all have complex three-dimensional networks, and we represent them too with their empirical formulas. That is just their single elemental symbol. Okay, so the metalloids, let's come back to the periodic table. They're saying the metalloids are all going to exist as three-dimensional networks, like crystal structures. So I would assume then that these post-transition metals would also exist as three-dimensional networks as well. So, but they don't say anything about that officially, but you get the idea. In general, it's not going to be until you get to the non-metals, at least when it comes to just pure elements, that you're dealing with discrete molecular units. But we again though we are talking about at standard temperature and pressure, or at least close to standard temperatures and pressures. If you were doing a reaction in a plant and the reactants were coming in at a very different temperature and pressure than standard temperature and pressure, and then you having this reaction take place, well, then you'd have to look and see, okay, well, what's the stable form of sulfur and oxygen or and whatnot at this temperature and pressure, and then that's what you would put as the reactants. Okay. Electron configurations of cations and anions. So yeah, it's easy to get used to electron configurations of elements strictly in their ground neutral states. But just remember, we do have cations and anions, right? We are going to have elements with different electron configurations because they're bonded to other elements, which we'll talk about in the next two chapters. So all we've taught when it comes to electron configurations up to this point, all we've talked about is the ground state neutral electron configurations of the elements, right? So like even with hydrogen, you could have an excited state of hydrogen. You could have a hydrogen atom with its one electron in the 3p orbital. That would be an excited state. Okay, and so what we're going to talk about in this section is, so you start with the neutral ground state configuration of elements, but in here we're going to talk about when these elements become cations or anions. So what is the ground state electron configuration of the cation or anion of an element? Right? So it's lost or gained one or more electrons and become charged. So because many ionic compounds are made up of monoatomic anions and cations, it is helpful to know how to write the electron configurations of these ionic species. Just as for neutral atoms, we use the Pauli exclusion principle and Hund's rule in writing the ground state electron configurations of cations and anions. We will group the ions in two categories for discussion. So, okay, that's interesting. If you're writing an electron configuration for the cation or anion of an element, nothing changes. You would go through the whole process of using the Pauli exclusion principle and Hund's rule and the Aufbau principle to do the electron configuration. Nothing changes. It's interesting. Okay, so we're going to look at ions. First, ions derived from the representative elements. Ions formed from atoms of most representative elements have the noble gas outer electron configuration. So yeah, if you're dealing with an ion of a representative element, it's what the representative element wants to form is the reason why it can create an ion is because it has a desire in some circumstances to have that noble gas configuration, the entire s orbital and p orbital of the highest principal quantum number filled up, right? The outer electrons become ns2 and np6. In the formation of a cation from the atom of a representative element, one or more elements or electrons are removed from the highest occupied in shell. The electron configurations of some atoms and their corresponding cations are as follows. So yeah, if we come to the periodic table, to get to the noble gas configuration, you can go in one of two directions. You can add electrons. You can imagine like oxygen and fluorine are going to want to add electrons to get to the noble gas configuration, or you can remove electrons. Like sodium and magnesium would want to remove electrons to get to the noble gas configuration. And so because with ions, the rules don't change as far as making the electron configuration, then it's really simple. It's just the sodium cation in A plus, its electron configuration is just going to be the neon electron configuration. It's that simple. Nothing changes, which is nice, right? The calcium ion, the cation, Ca2 plus, it wants to get to that noble gas configuration, is just going to be the electron configuration of argon. That's going to be its electron configuration. That is the electron configuration of the calcium 2 plus cation. And aluminum 3 plus, there's its electron configuration. So here's aluminum, right? But then whenever it loses the 3 electrons to become to get to that noble gas configuration, it's not like we have to rewrite some special electron configuration that's different, a little bit different than what we would expect. No, it's just going to be the electron configuration of neon for Al3 plus. Okay. In the formation of an anion, one or more electrons are added to the highest partially filled in shell. And so it's the same idea. The H minus anion, its electron configuration becomes helium. It just takes on the electron configuration of the corresponding noble gas. This is what happens with, again, we're talking about representative elements becoming cations or anions. All of these anions also have stable noble gas configurations. Notice that F minus, Na plus, and neon, and Al3 plus, O2 minus, etc., have the same electron configuration. They are said to be isoelectronic because they have the same number of electrons and hence the same ground state electron configurations. Right, so we're still, when it comes to these cations and anions, we're talking about the ground state. This is the most stable state of these cations and anions. We're not talking about excited states. So you can have a ground state electron configuration of a neutral element. You can have a ground state electron configuration of a cation or an anion, as opposed to, you would have with, let's say, H minus would have the electron configuration of helium, 1s2, but you could have an excited state of H minus where one of those or more of those electrons go up to like the 3p orbital. That would be an excited state of that ion, okay? But what they're saying is that, so even though H minus has the electron configuration of helium, it's not helium though, right? It's H minus. It has because it has one proton in the nucleus. It has the electron configuration of helium, but helium has 2 protons in the nucleus, whereas H minus has 1. So what they're saying is that to indicate that the similarity between these two substances, we see that they're isoelectronic. They're 2 different substances, right? One is H minus, one is helium, but they have the exact same electron configuration, so we say that they're isoelectronic. Okay, now what about the transition metals? With transition metals, we're dealing with cations. Metals form cations. In section 7.9, we saw that in the first row transition metals, scandium to copper, the 4s orbital is always filled before the 3d orbitals. Consider manganese, whose electron configuration is the argon 4s2 3d5. When the manganese 2 plus ion is formed, we might expect the 2 electrons to be removed from the 3d orbitals to yield the argon 4s2 3d3. Yeah. In fact, the electron configuration of manganese 2 plus is, so you remove the 2 4s electrons instead. The reason is that the electron-electron and electron-nucleus interactions in a neutral atom can be quite different from those in its ion. Thus, whereas the 4s orbital is always filled before the 3d orbital in manganese, electrons are removed from the 4s orbital in forming manganese 2 plus because the 3d orbital is more stable than the 4s orbital in transition metal ions. Therefore, when a cation is formed from an atom of a transition metal, electrons are always removed first from the ns orbital and then from the n-1d orbitals. Okay, yeah, so what they're saying is that we fill up the transition metals, the neutral atom, we do like the s orbital first, the higher principal quantum number s orbital, and then go into the d orbitals. So you would guess that, okay, well then, when it comes to forming an ion, a cation, you're going to remove the electrons first from those d orbitals. But no, when it comes to the transition metals, you're going to start by removing the electrons from that higher principal quantum number s orbital. That's a general rule. You can imagine there's nuances here and there, exceptions, but that's the general rule. When it comes to creating these cations from the transition metals, you start by removing electrons from that higher principal quantum number s orbital. And then from that one step lower principal quantum number d orbital. Okay, keep in mind that most transition metals can form more than one cation, and that frequently the cations are not isoelectronic with the preceding noble gases. Yeah. So it obviously gets more complicated when it comes to the transition metals. Transition metals can form more than one type of cation, and then as far as some, what are they? What is the resulting cation of a transition metal isoelectronic with? Well, that's not going to be as simple as with the representative elements. It's just being isoelectronic with the closest noble gas.